Hello, welcome to another module in this massive open online course. So, we are looking at problems on the analysis of LTI systems. Okay. So, we are looking at some example problems for that to illustrate the analysis and properties of LTI systems. So, before I proceed further, let me just modify the previous problem slightly. So, what I am going to do is, rather than making this integral minus infinity to infinity, I am simply going to change this to integral minus infinity to t, and now we can write this as, this can be written as the following thing. So, the impulse, so this can be written as integral minus infinity to t e to the power of minus j omega naught t minus tau ut minus tau. So, I can change the limits from minus infinity to infinity tau, because I am incorporating ut minus tau times x tau d tau. Now, you can see this is your h t minus tau, this is of course x tau, h t minus tau into x tau. So, this is h t convolved with x t. So, the impulse response is h t times impulse response h t is e raised to minus j omega naught t times u t. So, that is the impulse response. Let us note that down. So, a small correction, we have the impulse response h t equals e raised to power minus j omega naught t times u t. Now, to find the eigenvalue corresponding to e raised to s t, we note that this can also be written as the impulse response h t convolved with x t that is e raised to minus j omega naught t minus tau, or e raised to minus j omega naught, or let us write it this way, e raised to minus j omega naught t minus tau d tau x t d tau. Now, this I can also write this as x t convolved with h t, which means this I can write it as e raised to minus j omega naught u tau x t minus tau d tau. Now, since u tau is non-zero only for t greater than or equal to 0, so this can be equivalently written as integral 0 to infinity e raised to minus j omega naught tau x t minus tau d tau. Okay, just equivalently writing this as integral 0 to infinity e raised to minus j omega naught tau x t minus tau d tau. And now, I am going to substitute our function or signal x t equals e raised to the power of s t, and therefore, this becomes equal to zero to infinity e raised to j omega naught tau e raised to s, or e raised to s t minus tau d tau. So, we bring the e raised to s t common outside. So, this is integral 0 to infinity e raised to minus s, this is e raised to minus j omega naught minus s plus j omega naught tau d tau, which is e raised to st times e raised to minus s plus j omega naught by minus s plus j omega naught evaluated between the limits 0 to infinity. Now, at infinity this is 0 if s is less than 0, if s is greater than 0. So, this is equal to e power s t, and at 0 this is obviously 1. So, into 0 minus 1 by minus s plus j omega naught, but for this to be 0 s has to be greater than 0, that is e to the power of minus s has to be a decaying exponential. So, this is e to the power of minus s plus j omega naught tau. So, e to the power of minus s tau has to be a decaying exponential, which means s has to be greater than 0. So, this is basically reduces to e to the power of s t into 1 plus s plus j omega naught. This is the eigenvalue if real part of s is greater than 0. So, the condition required for this integral, real part of f is greater than 0. So, this is your eigenvalue corresponding to for the eigenfunction e raised to s t. So, this is the eigenvalue corresponding to the eigenfunction e raised to s t. Alright. So, we have constructed the impulse, so we have derived the impulse response of this system, the given LTI system, and we also derived the eigenvalue corresponding to the eigenfunction e raised to s t. Okay. So, let us look at another problem, which is to determine the differential equation describing a system, that is systems described by a differential equation. For instance, consider this system where I have, let me draw a schematic of a system. So, this system is x t and I have an error signal and this is an integrator. And the output of the integrator is fed back and subtracted from the input to give the error signal, and it is scaled by, this is multiplied by a scaling constant. This is a multiplier. Okay. So, this is a schematic diagram of a system, and let us try to determine, now what we are asked to do, we are asked to determine the differential equation representation of this system. So, we have to determine the differential equation the differential equation representation of the system above, and you can see we have basically x t minus E t, okay, x t minus alpha times y t equals E t. Okay, so we have that. Similarly, E t is passed through an integrator to yield y t, which means integral 0 to t e tau d tau equals y t. Now, what we are going to do? We are going to differentiate both sides of above equation. So, we are going to differentiating So, differentiating both sides of above equation, we have E of t equals d dt of y of t, okay, which means if I substitute this over here back over here, that gives me x of t minus y of t equals dy t dt, which basically implies that d dt y t plus alpha y t equals x of t. So, this is the differential equation. Okay, so, what we have is d dt y t d or dy t dt plus alpha times y t equals x t. This is the differential equation describing the above system. Okay, so, this is the differential equation. This is the differential equation describing above system. Okay. So, now let us try to solve this to get the output response. So, let us consider as another example the same system that we have derived above. Consider system above, which remember is described as d dt y t plus alpha y t equals x t, okay, and auxiliary condition. Remember, to describe the system, the auxiliary condition is y naught equals y naught, and corresponding to the input x t equals c e power minus b t x t equals. So, this is basically your input signal. This is basically your input signal. We have the auxiliary condition y 0 equals y naught, and we have the system that is described by the differential equation dy t dt plus alpha y t equals x t. Okay. And the way to approach this, as we have already seen before, is that the solution to any differential, the solution or the output y t to any system described by this differential equation can be described as the sum of two components y p t and YHT, where YPT is the particular solution and YHT is the homogeneous solution, okay, or YHT is the homogeneous component. So, we have seen that YT can be expressed as YHT YPT, where this is the homogeneous solution and this is the particular solution. And therefore, now for the particular solution, now what we are going to do is to find the particular solution. We are going to start with the assumption that YPT has the same structure as the input signal, that is k e raised to minus beta t. Now, we have dypt dt plus alpha ypt equals xt. This implies dypt dt is, you can see, minus k beta e raised to minus beta t plus alpha times k e raised to minus beta t, this is equal to xt. This implies that k times alpha minus beta e raised to minus beta t equals xt. This implies, or this is equal to, xt is given as k e raised to minus beta t. So, this is equal to k e raised to minus beta t. So, this implies this, or I am sorry, this is c. So, we are given xt equals c e raised to minus beta t. So, we have xt, the input signal is c e raised to minus beta t, correct, and therefore, we have alpha minus beta equals c. This implies, or k times alpha minus beta equals c, which in turn implies k equals c over alpha minus beta. Okay. So, we have the particular solution implies ypt equals c over alpha minus beta e raised to minus beta t. So, this gives us the particular this gives us the particular solution, which is c over alpha minus beta times e raised to minus beta t. We have found it by assuming the particular solution ypt to have the same form as the input signal, that is, it is the form some constant k times e raised to minus beta t, and this constant k has been subsequently determined as c over alpha minus beta. Let us now find the homogeneous solution. Now, to find the homogeneous solution, Now, let us assume y h t equals some k tilde e raised to s t. Now, remember the homogeneous solution can be found as by equating dy h t dt plus alpha y h t equals 0. So, now differentiating y h t. So, we have k tilde s e power s t plus alpha k tilde e power s t equals 0, which implies k tilde plus alpha e power s t, or which implies k tilde s plus alpha e power s t equal to 0, which implies s equals minus alpha. So, we have derived s equals minus alpha, which implies y h t equals k tilde e power minus alpha t. So, this is the homogeneous solution, but we have to remember still determine k tilde. At this point we still have an unknown, determine k tilde. And that can be done as follows. We have y t equals y h t plus y p t, homogeneous solution plus particular solution. So, this is k tilde e power minus alpha t plus c over alpha minus beta, c over alpha minus beta times c over alpha minus beta times e raised to minus beta t. Now, how do we determine the value of this unknown constant k tilde? And for that, remember, we use the auxiliary condition. Alright, so determine this constant. There is a single unknown k tilde. We have a single auxiliary condition, that is the value of the signal, output signal at time t equal to 0. So, I use the auxiliary condition to determine k tilde. So, what we can do now is basically use auxiliary condition to determine k tilde. So, we have y of 0 equals y naught implies k tilde plus c over alpha minus beta equals 0 implies k tilde equals minus c over alpha minus implies, I am sorry, this is equal to y naught implies k tilde equals y naught minus c over alpha minus beta. Okay. So, therefore, we have the solution y t equals y naught minus c over alpha minus beta e power minus alpha t plus c over alpha minus beta e raised to minus beta t. So, this determines the complete output signal. Output signal for given system, and also remember the auxiliary conditions are important. In In this case there is a single auxiliary condition, that is a value of the output signal y0 at time y0 at time t equal to 0, which is y0. Now for t less than 0, right, for t less than 0, since the input is 0, so the only output response, so for t less than 0 one can determine the output as follows. For t less than 0 we have xt equals 0, which means dyt dt plus alpha yt equals 0, and the signal that satisfies, the solution that satisfies this is again simply the homogeneous solution. So this implies yt equals, so let yt equals some s e power minus alpha t. So substituting this in this differential equation, we have minus alpha s e power minus alpha t. Okay. So this whatever one, now what satisfies this is basically, we already know that what satisfies this is the homogeneous solution s e power is of the form s e power minus alpha t, where s equals some constant, and now that you determine that by using once again the auxiliary condition y of 0 implies s equal to y naught. Okay. So implies s into 1 equals y naught, which implies s equal to y 1 naught. So for t less than 0 we have the output yt equals y naught e power minus t. So this is the output signal. So this is the output signal for at time t less than 0 when the input is 0. So you can think of this also as the 0 input signal. This is basically your 0 input signal. So you can think of this as basically this is the this is the output of the system when the input x t equal to 0. Now if you look at the output for t greater than 0, that can be expressed as y naught e power minus alpha t plus, well, let me write it down. I have that y naught minus c alpha minus b c over alpha minus beta e raised to minus alpha t plus 0 alpha minus beta e raised to minus alpha beta minus e raised to minus beta t for t greater than 0, which can be written as y naught e raised to minus alpha t plus c over alpha minus beta c over alpha minus beta times e raised to minus beta t minus e raised to minus alpha t, and you can now see that this is basically the y naught e power minus alpha t is the 0 input signal, that is output to when the input is 0, and this is basically known as the 0 state signal. So I can express the solution as y zit, which is input, which is output to 0 input, and this is basically 0 state signal, which is basically the response. So, this is the output to 0 input, or basically response to auxiliary conditions. And this y0 state is basically the response with zero auxiliary condition. So, basically you can see, you can express the solution yt also as yzit, which is basically the output to a 0 input, that is output signal when the input is 0, plus yzst, right, where zs denotes 0 state. So, the 0 state signal, 0 state output is basically output to 0 auxiliary condition, and you can see here that if y0 is 0, if the auxiliary condition is 0, y0 that is the output at time 0, that is y naught is 0, then yzi is 0, yzit is 0, it reduces to the 0 state signal, that is the output to 0 auxiliary condition. Similarly, if the input is 0, then we have already seen the output is basically yzit, which is basically the output simply to the the output to the 0 input, that is response simply to the auxiliary condition y at time equal to 0 is y naught. Okay. So, basically that completes this thing. So, I can express this as the 0 input signal yzit, which is the 0 input signal, plus yzst, which is the 0 state. So, this zs stands for 0 state signal. Okay. So, 0 state. This is basically your 0 state signal. Okay. So, we will stop this module here. We have looked at a couple of interesting example problems, all right, pertaining to basically the eigenfunction of an LTI system, the differential equation representation of a given system, and also the solution or the output signal to a system represented by a differential equation given the input signal and also the auxiliary conditions. All right. So, we will stop here and continue with other aspects in subsequent modules. Thank you very much.